let's introduce our first speaker. So we've got Ira Ktena, who is a staff research scientist at Google DeepMind, working on robust and safe AI with a focus on generative models. She completed a doctorate in medical image computing at the Imperial College of London under the supervision of Professor Daniel Ruckert. Her research focused on developing methods for modeling and analyzing graph-structured neuroimaging data at an individual or population level using traditional graph theoretical approaches and geometric deep learning. Ira visited the stroke group at Massachusetts General at Harvard, where she worked in the neurology group with Professor Natalia Ross, while being supported by an EMBO fellowship. So this will be a really nice talk. Looking forward to hearing it from you. So over to Ira.
Thank you so much, Tom, for the introduction, and thanks to the organizers for the invitation. I'll start sharing my screen. So hopefully you can see that now. I'll start with a little bit of background about myself. I guess it all started in academia, as it does for most of us. So I started my education back in Greece, where I'm from. I pursued a diploma in electrical and computer engineering, and this is where I got first taste of biomedical engineering, working on simulations and medical imaging, and started kind of understanding how algorithms can translate to societal impact. That led to me moving to the UK to pursue first a master's degree in biomedical engineering, where I specialized in neuroscience. And then I stayed on to pursue a PhD in machine learning and medical imaging at the computer science department at the same university. I spent a few months during the last year of my PhD on a short-term research fellowship in Boston, working in a clinical group. So my PI there was a neurologist, and she was spending a large chunk of her time actually seeing patients, and the rest of amount of her time she was carrying out research, which was a very interesting environment to be, and it was quite different by sitting in a computer science department and often coming up with our own problems that we had to solve. So after that, I moved on to industry, spent some time in an applied research group at Twitter UK, focusing on algorithmic transparency and personalization. And for the past about 4.5 years, I've been working at Google DeepMind, all of them in London, in the UK. And for the past 3 years, I've been focusing on safe and reliable AI. In terms of my time at Imperial, I guess the first exposure to research was towards the end of my master's degree, and then I spent a year as a research assistant in the lab that I later joined as a PhD student. So that was a way to get a taste of research and how it would be like to pursue a PhD. And I guess it was a positive experience, given that I decided to stay. And it was really during that time, I got lucky to collaborate with great researchers. The lab had good computational resources and connections to industry, which is not always the case. One thing that I guess I struggled with was that it was a relatively high pressure environment. The expectations were high to complete the PhD, and work-life balance could often be poor. But that was kind of counterbalanced by support from either postdocs or the cohort mentor that we had in our doctoral training program. In terms of my PhD journey, it was mostly focusing on graph-structured neuroimaging data. So I started my PhD being very curious about understanding how disease emerges and how we can study it with not necessarily like structural information, but also functional information. So starting off with more traditional graph, theoretical graph measures, and looking at the organization of the brain as it would emerge from diffusion or functional MRI data, and then connecting that to disease. And that actually later on came in handy when during my time in Boston, where we looked at a cohort of stroke patients, and we wanted to understand the connection between which parts of the brain were affected by the stroke and then the outcomes of those individuals. So if regions that are kind of highly operate as hubs were affected, then that would be reflected on the long-term outcomes of those patients. Then worked on identifying correspondences between brain graphs, given that there were different kinds of postulation methods. Some were group-based and other ones were tailored to individuals. And then in the latter case, it wasn't necessarily straightforward that we could identify which region in from one brain scan would correspond to the same region functionally in another brain scan. And then moving on to adopting more recent geometric deep learning approaches that were emerging at the time. So there were the first couple of graph neural network papers that had come out, and I started exploring how they could help us solve problems in neuroscience. And one of those problems was to measure similarity between graphs, and that was operating on individuals' graph data, or looking at the population then as a graph and then associating each individual with a node in this graph, and using the connections that capture some kind of similarity between those individuals in terms of phenotypic information in order to learn to predict the diagnostic labels with higher accuracy by leveraging those similarities in a semi-supervised way. So I guess a few other things that I got the chance to explore during my PhD outside of the university was volunteering in my community as a teacher and events organizer. There's this large community by the Anita Borg Institute that had local events, and that would include networking, mentoring, sometimes running hackathons. And that was a great way to explore, I guess, the wider London community in technology and STEM. But then I also got the chance to explore how industry is like with a research internship that was very different in topic to my PhD subject, and it was on music synthesis and audio generative models. So after that, I guess I was faced with a dilemma of academia versus industry, because there were things that I enjoyed in both environments, and that led me to joining a team that had been acquired by Twitter, and there were a few people I worked with previously in my lab in that team, and focusing on a new topic of fairness and algorithmic transparency that I found very exciting. before moving on to DeepMind, where I explored a few different research areas before converging, I guess, to things that I will talk about in a few minutes. And also, yeah, had the opportunity to engage in different initiatives for diversity in STEM and technology. So moving on to industry, I guess focusing on the past 4.5 years, I was very much kind of inspired by DeepMind's mission at the time, which was about solving intelligence to advance science and benefit humanity. So that was something that resonated a lot with my life goals and motivations. But then in practical terms, what I found was that this prior experience I had with working on brain graphs could translate actually to various different domains. I could see that graphs would emerge in different life sciences problems when exploring the signaling pathways of that constitute the hallmarks of cancer, or in protein folding, or even drug repurposing. This was one of the first works, if not the first one, that used geometric deep learning to identify basically a new use for an existing drug, which was quite revolutionary back in 2020 when it happened. So there was a lot of scope to apply techniques, I guess, that I had learned in neuroimaging and neuroscience to other domains in life sciences, but not only. Actually, the first project that I worked on at DeepMind was very different. It was on combinatorial optimization, and it had to do with finding better solutions to mixed integer programs that are problems that have this shape. There is an objective function with linear constraints, and the solutions need to be integrals. And these sorts of problems emerge in many different applications, like scheduling, packing, and even for like for energy, like in energy grids. And algorithms like this emerge to identify the best kind of distribution of energy along the grid. And the connection, I guess, to prior work was that there was a graph neural network involved. So there was a network that was constructed, a bipartite network, a bipartite graph, between the coefficients and the variables that we're looking to that are the solutions to these problems. And then a graph neural network would be used to assign to perform partial assignments, and so solve a sub problem of that original problem that would make it then much less costly and allow us to solve in multiple problems in parallel and identify a better solution than classical solvers would achieve with some other heuristics, for example. So it was quite a different application domain, but there were still techniques that transferred from that prior experience in neuroimaging. And then moving on to more kind of like safe deployment of health solutions. So this was a project that emerged actually from a product problem, and it was inspired by a Google product called Dermacyst, and it was a guided skin search tool that was powered by AI and would help people understand what is going on with their skin. So while the product would achieve high accuracy in the top 3 suggested conditions, then what the teams observed was that this was not necessarily consistent across geographical locations, skin tones, and age groups. So there was essentially a question of robustness and fairness of the model and potential biases that were inadvertently there because the original training distribution of the data was not uniform. So these are risks that arise when deploying such models, and it was not unique to this product. And they emerge from imbalance. They lead to imbalanced performance across groups due to the non-uniform distribution of the sensitive attributes. Or in other cases, there can be a performance drop due to unforeseen conditions. For example, there's a new type of camera or scanner, I guess, in medical imaging settings, or there can be a difference in the reference point of the images. For example, we've trained on clinician captured very high quality data, and then we move on to settings where the users get to acquire the images on their own. So it's quite different in quality. So we then, to solve this problem, we came up with this approach that was published at the beginning of this year at Nature Medicine, and then it would aim to make the most of available data by using a generative model to synthesize, to capture parts of the distribution that were underrepresented in the original training set. And that led to some high fidelity generation. But I guess the point of this session is not really getting into the technical details, but the last thing I wanted to capture was, I guess, a paradigm shift that we've seen, especially like starting from industry mostly, and then I guess now, yeah, it has affected both industry and academia, and then that involves moving from modality and task-specific formulations to generalist systems. So we used to have a segmentation model for the abdomen, a different segmentation model for brain regions, and not in the past couple of years mostly, things are moving in a direction where we have these generalist systems that then can adapt. They have they capture knowledge from different domains, and they can adapt to new settings quite fast, even quite often without even fine-tuning, but only at inference time by showing a few examples of a new problem. So that led to explore the use of vision language models for radiology report generation. So we started with 2D images and then moved on to 3D images, where it's even more benefiting, I guess, to use an AI system for that, given that it's much more time consuming to produce a report on 3D images. And again, this is where prior experience with medical data and MRI data comes in very handy, because you really need to understand what is the information, how the information is stored, how specialists read that information, and how to really enable them to build tools that are actually going to improve the efficiency of their workflow. So in terms of, I guess, some of the pros of industry that I experienced was better work-life balance, and working on applied problems that I didn't have the opportunity to experience in academia, flexibility, and I guess time management. But on the con side, then it's not a given that you get to always work on what you want, and you need to iterate faster on ideas and let go of them quickly if they don't work. And quite often you need to align with many different stakeholders that require different styles and levels of communication, while always incentivizing why you're doing a certain type of work and how it's benefiting the company. But I guess it's always possible to keep ties to academia. Couple of things I did to accomplish that was joining the advisory board of the doctoral training program that I started in at Imperial, writing a book chapter on machine learning in connectomics with a couple of other colleagues that was published last year. Organizing workshops at conferences and panel discussions, and working with external academic collaborators on topics that I find particularly interesting that may not be a priority, I guess, for my company. In terms of transferable skills, I found that approaching problems with curiosity, breaking them down to understand what it is that I need to understand first before solving kind of the bigger problem was definitely something that I gained from that experience of my PhD in this field. The motivation, the like having this drive towards scientific impact and rigor, and instead of trying to do things quickly without necessarily understanding why something would work or not work, spending the time to do this rigorously. Another thing that I found particularly helpful was working with messy data, especially when I worked with clinical data rather than research MRI data. That was like a very different experience, and also appreciating the value of reproducibility, because we don't want to, especially in the medical setting, we want to ensure that if we have very similar population acquired with a different scanner, we wouldn't completely change our conclusions and results. And also dealing with issues of scale. These images are very high resolution, have many slices quite often. So dealing with these challenges of scale has been particularly helpful. And that's all I had prepared for today. So if people have questions, then I would be more than happy to take the next few minutes to answer them.